I am Janine V. De Los Santos from Block 1, Gen Ed for Formative Assessment. Let's learn math in simplest way. Today, we are going to study mathematics in modern world. To begin, let us know the importance of mathematics in one's life. Mathematics helps predict behavior of nature and many phenomena, such as predicting the weather. It also helps in application in many human endeavors, like robots, MRI, and speech recognition. Some say it is a study of numbers and arithmetic operations. Did you know that mathematics is universal? Yes, it is universal. When we say universal, it is useful in every ways, like for example, the universal charger. It is applicable to all and it can be used to charge all different types of batteries, including those used in cell phones. That's one example of universal. Mathematics is universal because it can be used in our everyday lives and in everywhere or in any situations. Everywhere we can see mathematics, and every day we use mathematics. One evidence that can prove it are patterns. We can find pattern in living and non-living things, in structure, churches and leaves. We can find symmetry. In shapes such as star, we can find radial symmetry. In lime slice, we can find rosette patterns. Some patterns consist of Fibonacci sequence, invented by the Italian Leonardo Pisano Bigolo. It is process of adding two numbers to get the answers of the consecutive number. Fibonacci sequence can be found in flowers, branches, fruits, and vegetables. Patterns of nature. What is pattern? Patterns are regular, repeated, or recurring forms of designs. As we all know, and if we observe our surroundings, especially our own home or house, we will see pattern or nature in this world. We will see and know that it is the pattern. Types of patterns in nature. Number 1, symmetry. From the word symmetry, it is sim, which is same, and metry, which is measure. So it is same measure. Symmetry is the quality of being made up of exactly similar parts facing each other or around an axis. The American Heritage Dictionary defines symmetry as an exact correspondence of form and constituent configuration on opposite sides of a dividing line or plane, or about a center or an axis. In mathematics, an object is said to have symmetry when it remains unchanged after transformations, such as rotations and scaling are applied to it. Symmetries has different kinds and they will be discussed in the next section. Example: starfish. Picture of Leonardo da Vinci, or parts of the body like legs and arms. Virtuavian man. It shows the proportion and symmetry of the human body. Number 2, fractals. Fractals are persistent patterns which are self-similar across different scales. This means that zooming in the lens onto the object's digital image, fractal, does not provide specifics of a new view, but just the same as the original image. The image clearly reappears again and again, no matter how many times the object is magnified. Examples of fractals in nature include mountain ranges and heart rates. Number 3, spirals. Spirals are curved pattern rendered around a central point by series of circular shapes. The spiral pattern, like fractals, is very common in nature, from the biological molecules that make up humans to the body plans of some plants and animals to typhoons and galaxies. Some examples showing the spiral patterns in nature can be seen in snail shells and typhoon satellite images. Number 4, chaos. Chaotic patterns or chaos are basic patterns generated from underlying complicated behavior. Unlike common concept that relates it to the total chaos, a chaotic pattern is used to define a sort of order that lacks predictability. Chaos reveals that the underlying patterns, continuous feedback loops, repetition, subsimilarity, fractals, self-organization, and programming dependency at the initial stages. The apparent randomness of chaotic and dynamic systems and the unpredictable and unstable processes that occur. Chaos frequently involves fractals. Example of chaotic patterns in nature can be seen in cloud street tornadoes and lightning. Symmetries of our surroundings. Throughout our daily language, we refer to symmetry as a sense of balance and proportion that is harmonious and beautiful. As what was said earlier, when an object stays unchanged, it is said to have symmetry. After transformations, such as rotations and scaling, are introduced in it. Nature is packed with patterns with particular symmetries, with various kinds. Number 1. Reflection symmetry. Often known as mirror symmetry or line symmetry. Reflection symmetry is made by a line going through an object, splitting it into two parts that are one mirror images of the other. This is also called bilateral symmetry, since it splits the object into two. Bi means two mirror images. Number 2. Rotational symmetry, also known as radial symmetry. In biology, objects show this kind of symmetry when their identical parts are consistently arranged around a central axis and the pattern looks the same after a certain amount of rotation. Objects and species that exhibit radial symmetry bear a similarity to a pie that contains similar parts after many lines or planes have been removed. There are no left or right side to some of these objects or organisms. However, some sources say that rotational and radial symmetries differ from each other. because they do not need to shift or rotate radial symmetries to demonstrate their symmetry. Number 3. Translational symmetry. This type of symmetry is demonstrated by objects that do not change their size and shape, even though they move to one another or they move to another place. Remember that reflection or rotation is not involved in the movement. Fibonacci number. The Fibonacci numbers were first discovered by an Italian mathematician named Leonardo Pisano. He is famously known by his nickname Fibonacci. Fibonacci sequence. The Fibonacci sequence is a series of numbers in which each term is the sum of the two numbers preceding it. It is defined by the recursive relation defined by the equations. The Fibonacci sequence can elaborately write as the golden ratio. Golden ratio is among the best known and most popular numbers that are studied in mathematics, and ancient Greeks gave it mystical properties and called it the divine proportion. And over the years, the number has taken many different names: the golden number, the golden section, and in modern times, the golden ratio, which is the name we use until now. Determining the golden ratio is by picking one Fibonacci number from the series and get its ratio to the number that comes before the number you chose in the series. Example: mathematical language and symbols. Mathematics all over the world is the same despite the difference in language we use. Mathematics will remain the same. Therefore, it can act as our universal language. Mathematical phrase or formula has the same meaning, regardless of the language used. To explain it, mathematics makes people understand and connect in this way, even though there are other communication barriers. English language versus mathematical language. Every language has its own vocabulary for words, and its rules for combining such terms into full thoughts or sentences. Mathematics isn't exemptions. Before we fully understand the language of mathematics, we should have a better understanding on the distinction between mathematics noun, it used to name mathematical objects of interest, and mathematics sentence, it states full mathematical thought. Writing expression and equation. An expression is a number, a variable, a combination of numbers, and variables And the symbols of operation and an equation consist of two terms or expressions which are connected by an equal sign. Translate the mathematical expression or equation into English phrase or sentence. So this is the mathematical equation. What do you think is the English sentence of this? Possible answers. 5 minus the sum of twice a number and 8. 5 less the sum of twice a number and 8. The sum of twice a number and 8 less than 5. The difference of 5 and sum of twice a number and 8. Translate English phrase into mathematical expression or equations. 27 less than negative 15. What do you think is the answer? Great job! That's the answer. That is now the mathematical expression of that English sentence. Problem solving and reasoning. A great solves a great problem, but there is a grain of discovery in the solution of any problem. Your problem may be modest, but if it challenges your curiosity and brings into play your inventive faculties, and if you solve it by your own means, you may experience the tension and enjoy the triumph of discovery. By George Polya. Inductive reasoning. The type of reasoning that comes up to a conclusion by examining specific examples is called inductive reasoning. A conclusion that is made by applying inductive reasoning is called a conjecture. Conjectures may or may not be correct. Inductive reasoning may be used in many life situations. It is specific to general. A great example of inductive reasoning is the process a child goes through when introduced to something new. If a child has a dog at home, she knows that dogs have four legs and a tail. If a child were to be introduced to a cat, that child may very assume that cat and dog is the same. Why? Because the cat has four legs and a tail. In the child experience, this means dog. The child induces from her specific scenario something about a much larger population. Another example is this. Deductive reasoning. Deductive reasoning, unlike inductive reasoning, is a valid form used in proving observations and arriving at conclusions. It is a process by which one makes conclusions based on previously accepted general assumptions, procedures, and principles. It is general to specific. Example: all dolphins are mammals. All mammals have kidneys. Therefore, all dolphins have kidneys. Problem-solving strategy. One highly acceptable problem-solving strategy is designed by George Polya. The basic problem-solving strategy that Polya advocated consisted of 4 steps. Polya's 4-step problem-solving strategy. First one is understand the problem. Number 2, devise a plan. Number 3, carry out the plan. Number 4, review the solution. There are 900 residents of Santa Rosa, Laguna tested for COVID-19. 75% of them are negative. 160 has found asymptomatic and the rest have resulted positive for COVID-19. How many residents have tested positive for COVID-19? Step 1. Understand the problem. How many residents have tested positive for COVID-19? Step 2. Devise a plan. Given 800 residents, 75% is equals to negative, 160 is equals to asymptomatic, and positive is missing. Step 3. Carry out the plan. 800 is equals to 100% total. 160 resident is equals to 20%. 160 divided by 800, that could be 20%. 75% equals to 600 residents. 800 times 75% is 600 residents. 100% minus 20% minus 75% is equals to 5% positive. 5% is equals to 40 residents. 800 times 5%, that could be 40 residents. So therefore, step 4, review the solution. Answer: there are 5% or 40 residents out of 800 residents have tested positive for COVID-19.